We present a method for real-time depth refinement for specular objects. Popular depth scanners such as the Kinect, Intel RealSense, and so forth cannot capture high-quality depth profiles. A common approach for refining depth maps is to use the additional details in the intensity images provided by such scanners. Previous works have been able to enhance the surfaces in real time using a Lambertian reflectance model. However, once these methods are applied to specular objects, artifacts are introduced in the areas of specularity which cannot be accounted for by the Lambertian assumption. In our approach, we propose to exploit the known calibration of the infrared camera and projector in order to obtain a controlled lighting scene from which we can explicitly model the specular phenomena and improve the depth quality in real time. We note that for infrared cameras in such scanners, the main source of lighting is the scan projector. Our algorithm takes a rough depth map and an infrared image as inputs. As a pre-processing stage, we smooth the depth map and calculate the surface normals. We then estimate the scene illumination with our novel lighting model, which consists of three main stages: calculating the diffuse and specular shading maps, recovering the specular albedos, and recovering the diffuse albedo. The refined depth map is then obtained by an optimization process that finds the best fit between the depth map and the IR image. We tested our method on several synthetic scenes and on real scenarios. In the armadillo scene, we can clearly see how our method outperforms the competing methods as the other frameworks introduce geometric distortions in specular areas. In the Greek statue example, we can see the improved quality of our reconstruction compared to the other approaches. Zooming in, we see the specular artifacts of the other methods. The pumpkin example examines how the three different methods handle a multiple albedo object with specularities. Our framework more favorably reconstructs the object without geometric distortions. The cheeseburger scene presents a partial failure scenario for our method. The front sesame seeds are incorrectly mistaken for specularities by our lighting model. This is because the missing sesame seeds are located in an area which is prone to specular reflections and consists of sparse blobs that are much brighter than the diffuse and ambient lighting approximation. Therefore, the surface geometry is not updated in those areas. Despite this, we can still see the improved depth quality of our method in the other specular areas compared to the other methods. We now present a real-time example of our framework. Our GPU implementation runs at approximately 12 frames per second. We compare the result against the method of Orel et al. From CVPR 2015. Rendering this scene with a shader that enhances high curvature areas, we get a clearer view of how the surface distortions are correlated with the location of the specularities.